Hi, everyone. Welcome to Stat 243. I believe this is lecture 9. It might be lecture 8. I'm not doing this in class today because we're taking a quiz, so I'm just recording this myself. I may replace this with the lecture that I record during class. And we are talking about OpenStax, Chapter 6, the Central Limit Theorem. So let's start by reviewing a bell curve, also known as a normal distribution. So a bell curve, which looks something like this, right? Technically it goes on forever, but we give up after a while and we just stop the curve. And this one is not quite symmetric because my angle is a little off. But let's pretend it's totally symmetric. If this is a probability distribution for a random variable x, then the center of our bell curve is our expected value of x. So one thing I want you to notice about this bell curve is that observations near the expected value are more likely, and they get less and less likely the farther the observation is from the expected value. And that basically tells you exactly what a bell curve looks like. It's a probability distribution where observations near the center are likely and observations far away from the center are not likely, and they get less likely the farther you go. If you have a distribution with this characteristic, it's similar, if not exactly equal to a normal distribution. And we're going to use this fact to build up our central limit theorem, which is a super useful tool for doing statistics. Okay. All right, so let's look at an example. Let's take a probability distribution that's not going to be normal. Let's say it goes between 2 and 12. And it looks something like this. Now, this distribution, it can still be a probability distribution, but notice that values toward the center are not likely and values toward the edges are more likely. So this is not a normal distribution, but it still has an expected value. To me, it looks like it's right about here, which is what you get if you were to balance this distribution on the point of a pen. You need to balance it right about there so that it all balances okay. Now, if we want to understand this distribution, we could look at just a single observation. But that doesn't tell us very much. If we don't know anything about the rest of it, a single observation doesn't tell us much about the distribution. So instead of looking at a single observation, let's use the old data trick of collecting more data. And let's look at the mean of a sample. So these are going to be X bar, the mean of a sample. If that sample is large enough, say 30, then it's going to be a reasonable way to understand this distribution. The expected value of X is the value that you expect to be close to if you compute the mean of a sample. Well, that tells us that if I take a mean, or if I take a sample and I collect the mean, then probably I'm going to be pretty close to this expected value of x. Not exactly right, but pretty close. And if I do it again, I might be pretty close again. I'm not going to be exactly right, but if my sample's big enough, I should be pretty close most of the time. Of course, sometimes I might be a little bit farther away. And I could be very far away once in a while. It's not likely, though, because if I were very far away, that would mean that all of my observations came from far to the left. One observation down here, not so surprising, but all of them down here and none of them up here would be surprising. So my sample means are generally going to be close to the center, and they're going to be less likely the farther away from the center I get. And that is exactly how you describe a normal distribution. So to write this down and say it again, the sample means from different samples, whether it's a probability distribution or a population, the sample means are generally going to be close to the expected value of x and are less likely the further they are from the expected value of x. Put another way, and this is the mathematical way, no matter what the distribution of the random variable x is, the distribution of sample means x bar will be approximately normal if the sample is large enough. Usually that means 30 plus. There are a couple cases where even less than 30 is okay. Take any distribution, right? It can look very far away from normal. But if you collected a bunch of samples and did a histogram of those sample means, that histogram will look approximately normal. I want to show you what that looks like in R, and then we'll talk about some of the useful consequences of this theorem. And by the end of this lecture, I'll write down this theorem in its more formal way. Let's jump over to R and RStudio. So here is a histogram of April temperatures according to the climate data. It's not a normal distribution because it's not a nice bell curve. It's not too far away from a normal distribution, but I would not call this one normally distributed. However, it does have an expected value. It has a mean, which is a little more than 16. Right? The balance point of this histogram is right about here. Now let's take a sample of that climate data. Let's take 50 observations, nice and big. And we're going to allow ourselves to choose the same observations more than once because we're treating this population like a probability distribution. Here's our sample. And it just is a bunch of different observations of temperatures, right? Here's 22.2, there's 22.2 again, so you can have the same observation more than once. And if we look at the mean of that sample, 13.76. So it's not exactly equal to 16.3, but it's fairly close. And we can do this again. We can do another sample and look at the mean of that sample. That one's 16.4. That's super close to the expected value, which is 16.3. And we can do this again. But why don't we leverage the power of R and do this 10,000 times? And what I'm doing right now is writing some code. So I'm saying I'm going to have a collection of 10,000 sample means, and I'm going to populate it with the mean of each of those samples. And then I'm showing you writing out the code rather than just having it pre-populated mostly because if I make a mistake, you'll see that no matter who you are, you make mistakes when you write codes. Let's see. Okay, it seems like it ran. Let's take a look at the raw list of sample means. There's a whole bunch of numbers, but guess what? A lot of those numbers are pretty close to 16.3. Some of them are farther away, but most of them are pretty close. Let's look at that histogram of those sample means. And what do you know? It's almost a perfect normal distribution. The temperatures themselves are not normally distributed, but sample means are generally going to be close to the expected value and are going to be less likely the farther away from the expected value you are, and that is what a normal distribution is. In fact, the center of the sample means is 16.35 as opposed to 16.34. And really, they're the exact same if you do your rounding correct. So that is what the central limit theorem does. Through the power of collecting more data, we can go from a continuous, actually any distribution that is not normally distributed, and turn it into a distribution that is normally distributed, as long as we're looking about means of a sample instead of individual observations. Here's what would happen if I didn't collect very many samples. Let's just do 5 and let's do 100. So I'm going to take my distribution here, but my samples are going to be really small. They're only going to be 5 observations. And I'm only going to do that 100 times. And when I do it 100 times, it's a little more normal than the original, but it still is not very much like a true normal distribution. So how do I improve my probability distribution? I collect more data. Instead of collecting 5, let's collect 30. And even with just 30, that one's not super normally distributed, but let me do that 1,000 times. And now we're already looking a lot more normally distributed. Okay. So back to the notepad. No matter what the distribution of the random variable x is, the distribution of sample means x bar will be approximately normal if the sample is large enough. what does this do for us? Well, the main thing it does is we have really good tools for working with normal distributions. In particular, the tool that we like is the number of standard deviations maps really well to probabilities. And probabilities are how we make decisions in statistics. But this mapping from standard deviations to probabilities, it works much better with normal distributions than any other kind of distribution. And so, through the power of data, the power of collecting more, or at least enough data, we can create a useful normal distribution that we can then use our tools on. I can't use normal distribution tools on this distribution because it's not bell-shaped. 2 standard deviations away from the center is not going to tell me where 95% of the data lives, probably. I would be lucky if it did. But if I collect data and average it, 2 standard deviations on this graph will show me where 95% of the sample means live. And that is really good information about my population. All right, the central limit theorem formalized. Let X be a random variable, mostly going to be a continuous random variable, or at least a quantitative random variable, with an expected value, expectation of X, and a standard deviation stdev of X. I'll draw the picture. Here's my distribution of X. I'm not going to worry about the numbers right now, but let's say it looks like that. It's not normal, but it's a random variable, so there's an expected value, let's say right here, and there is some kind of standard deviation. It just doesn't tell me probabilities quite so easily. So if we have this condition where X is a random variable, it has an expected value and a standard deviation, then if you collect a random sample of size n, where n is large enough, n is usually at least 30, the averages of those samples, X bar, will be normally distributed. That's the first useful consequence. Even if your probability distribution isn't a bell curve, your sample means, averages, means, your sample means will be normally distributed. But there's more. We also know the expected value of the sample means, not of an observation, but of the sample means. Where do we think those sample means will be? We write that as expected value of X bar. That's going to be the exact same as the expected value of X. Expectation of X bar equals expected value of X. We saw that with our R example, where the expected value of the temperatures was 16.3, but also the expected value of the sample means was 16.3. And we get one more piece of information out of this, because a normal distribution has an expected value and it has a standard deviation. The standard deviation of the sample means. This is stdev, not of X, but of X bar, is smaller than the standard deviation of X itself. Our sample means are going to vary less than our observations. And we have a mathematical formula. stdev of X bar is the standard deviation of the random variable, stdev of X, divided by the square root of the sample size. So just to write it using the letter, xtdev of X bar is equal to S over the square root of n, where S is a standard deviation of the random variable. I'm going to come back to R and I'm going to show you what this piece means. The standard deviation of the sample means is smaller than the standard deviation of X. So let's see why that's true using R. I'm going to erase some of these. Yeah, sure. Okay, so here is the histogram of our climate data. It ranges between about 0 and about 30, right? So it's got a range of about 30, and the actual standard deviation of our climate data is 7.6. And that can make sense, right? If you start here at 13 or 16 and you go up 7.5 and another 7.5, that gets you up around 30. If you go down 7.5 and 7.5, gets you around 0. If I look at my sample means, and here we're going to do a sample size of 50, and we're going to do a distribution with 10,000 of those. It's still centered at 16, but now it only ranges from like 13 to 19. The range is a lot smaller than the range of the actual observations. You can have a city that's super cold. That makes sense. A city that's 0 degrees Celsius in April. But to have all of your cities be around 0 degrees, that you would never expect to happen. Because a random sample should take some that are 0, but also some that are 10, and also some that are 20, and also some that are close to 30. And when you average all that, it should bring you back to the expected value. One city that has 0 temperature, not surprising. All 30 cities close to 0 temperature, very surprising to the point where you don't think it would ever happen. Sample means close to the expected value occur most of the time. And the farther away you get, the less likely they are. And we can actually see what that standard deviation is. Remember that the standard deviation of our climate data was about 7.5. The standard deviation of our sample means is only about 1.08. It's a lot smaller than the standard deviation of the sample. And if we check our formula, the standard deviation of our sample means should equal the standard deviation of our sample divided by the square root of the sample size. So let me take the standard deviation of the sample, climate data, $temp, and I'm going to divide it by the square root of our sample size, which is 50. Let's see what that number is. Aha, just about the same, 1.08. Now, the reason it was so close is because there were 10,000 samples and they were pretty big, 50. If you don't have that many samples, you won't be so close to the theoretical calculation, which is this one. But we got lucky. So hopping back to the notepad one more time. Let me just draw this more schematically using, again, that same probability distribution. I'm not worrying about the numbers so much. High, then low, then a little bit higher. Okay, so this is the distribution of X, and we're going to collect samples that are big enough in size to apply the central limit theorem. So this is going to be the distribution of sample means, X bar. Here's our expected value of X right there. If I collect a sample, I'm going to have some observations below it, some observations above it, some observations close to it, and they're going to average out to be close to the expected value of X. And most of them are, especially if my sample is going to be big, like 30 to 50 or more. And every once in a while, I might have a sample that has a lot of really small observations or a lot of really big observations. And so it's going to pull my sample mean farther away. But still, most of the time, I'm going to be very close to the expected value. This is the expected value both of X and of X bar. And the spread from my top distribution, it's pretty big, right? So two standard deviations might be like this. But the spread down here, the standard deviation of my sample means, that's going to be much smaller because they're clustered much more closely to X, the expectation of X bar, which is the same as the expectation of X. Let me do one example using some numbers, and then we'll be done with our video for today. The population of penguins. Has, do I want a population? Yeah, has an expected weight of, let's say, 2 kilograms with a standard deviation of 0.4 kilograms. Would you be surprised, statistically speaking, if a penguin weighed 2.6 kilograms? Well, 2.6 kilograms is only 1.5 standard deviations above the mean. So that's not surprising, right? Using our 2 standard deviations rule of thumb, this is not surprising. This is not an extremely high weight. Let me rewrite the parameters. Population of penguins. Expected value of the weight was 2 kilograms. Standard deviation for the penguins themselves was 0.4 kilograms. Now collect a sample of 36 penguins. The average weight is 2.6 kilograms. Is that surprising, statistically speaking? Well, as soon as we talk about the average, we're talking about X bar. So now we build a normal distribution with an expected value of X bar, which is the same as the expected weight of any given penguin. That's 2 kilograms. But the standard deviation of those means should be smaller because a sample stabilizes estimates. It should be the standard deviation of the X, but divided by the square root of the sample size. So it should be 0.4 divided by 6, which is close to 0.7. It's like 0.66. Yep, 0.66 kilograms. 0.066 kilograms. So the surprise, to answer the question, I ask how many standard deviations of the mean is 2.4 above the expected value of the mean. Well, regardless of exactly what the population of penguins was distributed, I know the distribution of average weights is normal because of the central limit theorem. The center should be 2.4, and each standard deviation, it's not 0.4, it's 0.066. Or let's make it simple and say 0.7, which means this one here is 2.47. This one here is 2. Oh, sorry, this should be 2.0 exactly. 2.0 is the center. So 2.07 here, 2.14 kilograms there. And we're talking about 2.4 kilograms. That's way out here. One penguin that weighs this much, this is 2.6 kilograms. Sorry, I'm getting my numbers wrong. A sample of 36 penguins that average 2.6 kilograms. One penguin that weighs that much is not surprising, but all 30 penguins in the neighborhood of 2.6 kilograms would be completely unbelievable. So yes, we would be statistically surprised. Okay. So your lab 2 asks you to do this process with some of the continuous style data from your particular data set. You get to look at a single observation and ask if that's surprising, and then you get to look at the sample mean and ask if that's surprising. I'll also probably repost these notes now that I've got a first crack at it. I wanted you to have these on time, but I'll repost these Friday morning once I do the lecture in class if I think that the lecture is going to be more informative. So thanks for watching. Have a good evening.